see today that how inductor can store energy. Now, the thing is as I told you, suppose you apply any voltage, time varying voltage across an inductor plus minus V t, and then allow a current to, suppose current at any time t is I, then what is the voltage across the inductance? It will be, this is plus, this is minus L d I d t, is not. Now, if you look at the inductor, voltage across the inductor is L d I d t with this polarity and current is entering through plus. Therefore, it is going to absorb power. So, power absorbed, instantaneous power absorbed at any time t, it is absorbing a power which is the voltage magnitude L d I d t into the current. This is the amount of power at any time t the inductor is absorbing. Now, therefore, if you consider a small amount of time dt, energy, I will write it. Now, energy supplied to L, to the inductor over a time dt, dt as you know tends to 0, a small perturbation over a time dt will be nothing but dw, elemental energy that is fed to the inductor is that it will be L d I dt into this I into dt. This will be the thing, which then dt is vanishingly small, no doubt, but not equal to 0. Therefore, you can cross these two out because of that reason. So, it will be L I d I, this will be the energy at dw. Therefore, what will be the energy at any time t? So, energy, total energy supplied to the inductor at time t, energy supplied total energy supplied to the inductor, you have to integrate this one. Now, the question is what limit should I put? Limit I should put depending upon the fact that is, suppose the initial current was 0 and final current is I, some current I. Therefore, it will be half L, or I should write any current, whenever it is carrying any current, suppose this is I, it does not. So, half L I square, this is the energy supplied. Where is that energy gone? You will find, to your surprise, the conductor, since it has got not resistance, of course, you should not touch with hand, but even if you touch, you imagine that I am touching the bare conductor which has made this inductor possible, you will find there is no heating effect, because I have assumed R equal to 0, some ideal situation of course. In a practical inductor there will be little heating, because there will be some small resistance, however small it is, but I am telling you in this ideal situation, okay, you will find there will be no heating effect. then where that energy gone? This energy will be stored in the magnetic field. As I told you, since you are passing some current at any given time t, if the current is high, Ni by L is H into mu is your B, and you know the magnetic field B square by 2 mu 0 etcetera, that is a measure of the energy stored per unit volume. Therefore, this energy will be stored in the magnetic lines of force. Okay. Therefore, whatever energy I have supplied, it has not been lost, but it will be stored in the inductor. So far as the circuit thing is concerned, we will not go to the level of flux lines. I know what it is, but one must know that it is stored in the magnetic field, this much, but it has the capacity to store the energy. The idea is we store several things in our houses. Similarly, it looks like energy can be stored in an inductor, and perhaps by doing some intelligent circuit, I will now I have got plenty of energy, I will store it in the inductor, and whenever I will need that energy, I will take that energy from the inductor and use in my practical situations. That is the whole idea. In fact, power electronics nowadays depends on inductor and capacitors. Their energy storing properties makes all the power electronic circuit possible. Okay, sometimes stored energy in the inductor, whenever at opportune time you extract the energy from the inductor, do this at a fast rate, things like that. But nonetheless, the point I want to make, if you know the for example, if the value of the inductor is equal to 2 Henry and current at any time t you find it is 5 ampere, then what I am telling, the energy stored by the inductor will be half L into I square. It will change with time. Instantaneous value of the current square into half L will give you the energy stored at that time. So, suppose at a particular time you notice it is 5 ampere 2 Henry, then I will say it is 25 joules. So much energy it is storing. Got the point? Achha, I will tell you another interesting thing here, because this problem I have already indicated to you. Suppose you have an inductor. Let me put some numbers so that you feel easy with the problem. Suppose I will do it slightly differently. Suppose it is 10 volt. Suppose the value of the inductance is 2 Henry, and here this problem you try to understand. Here is a switch and here is another just wire having no resistance. This switch can be moved, has 3 positions. One is in this position when this terminal is suppose A, this terminal is B. S is neither connected to A not to B. Achha, if this circuit is left like that, what will be the current in the inductor? 0, open circuit, how current can flow. That is, I have not applied across the inductor any voltage before that. Now, what I will do is this, look carefully, at t equal to 0, I will move the switch, to position A. So, if you do that, then your circuit at t equal to 0, you have done it like this. So, for t greater than equal to 0, this is the circuit and this inductor is 2 Henry. Therefore, I want to find out what will be the expression of the current in the inductor. How do I do it? I know that I 0 minus in this case is equal to 0 and that must be equal to I 0 plus. This is the crucial thing, and I 0 plus and I 0 is 0. Then I will write that say V is equal to L d I dt, whatever way you write I, and this is a constant value, that is 10 volt, or L is 2 Henry. So, 2 d I dt is equal to 10, or d I dt is equal to 5, or I is equal to 5 t if you integrate plus some constant of integration. This is another way of doing it. So, I is equal to 5 t plus A, and this value of A I will find out from the initial condition. Here I 0 minus, I 0 plus, which is also I 0 for all practical purposes. Therefore, I apply this condition and find out the value of A. So, I 0 being 0, therefore, A must be 0 and your I is equal to 5 t. And we have seen that if you plot this current against time I t, it will rise. What is the slope? Slope is, this is the rate or m slope of this curve. I have drawn it wrongly like 45 degree, it is not like this, 5 times more. So, for this particular problem it was doing like this. This is I equal to 5 t. And as I told you, you should not be careful. I mean, you just do not leave the circuit in this position forever, then your inductor will be spoiled, because soon it will cross the rating of the inductor current and spoil everything. Okay, so, it is like this. Therefore, suppose at now this is the switching I have done at t equal to 0, move the switch to position A. Now, what I do at t equal to 2 seconds, move the switch from position A to position B. So, at t equal to 2 second, so at t equal to 2 second, if you just this is suppose 2 second, 1, 2, then this current will be 10 ampere. Why this 2 second was chosen? Most probably it was the rated current of the inductor. I will not allow under any circumstances to pass a current which is greater than 10 ampere, that is why perhaps this 2 second has been chosen. Anyway, you do not bother about that. At t equal to 2 second, current through the inductor will be 10. And after that, at t equal to 2 second, I move the switch from position A to position B. Therefore, for t greater than equal to 2 second, circuit will look like this one. It is shorted. This current is IT, inductor current, and this is L equal to 2 Henry, is not t greater than 2 second. This is the fate of the circuit. Therefore, current at t equal to 2 minus, see here I am doing a switching. Try to understand, t equal to 0 minus is not a very, I mean not always that thing will happen. Okay. At t equal to 2 you are doing some switching now. So, you have reached t equal to 2 second. So, current at t equal to 2 minus is what? 1.99999 whatever it is, very close to 2, but not equal to 2. That current was equal to 10 ampere, is not? That will be the current. Now, the question is what will be the current at t equal to 2 plus, just immediately after 2 seconds. Current through the inductor cannot change instantaneously. Therefore, if in the red curve blue curve, if you sketch the current, I will sketch it separately here, that is nicely it can be sketched with a red color I will draw. So, it went up to 10 ampere current, this time was 2 second, this axis is time. So, t 2 minus current was 10 ampere. What I am telling, after you have done the switching, move S to B from A, then also current has to be 2 ampere immediately after this, 2 ampere. Is not, that has to be this one. So, but what happens say at t equal to 3 second, 4 second, like that? Nothing is surprising. Now, for t greater than 2 second, I will once again write down the KVL equation here. What is the KVL equation? Plus minus L di dt, is not? This is the KVL equation of this circuit. Applied voltage is 0. So, I will see for this circuit, I am writing the equation. I will write L di dt is equal to your 0 applied voltage. Now, the voltage applied here, no voltage exists between these 2 points, L di dt 0. If L di dt is 0, di dt must be a constant number, I must be a constant number, which means that is L y I am writing 2 di dt, 2 di dt is 0, which implies that di dt must be a constant, is not? This must be the constant. I must be a constant, I am so sorry. I must be constant. So, for t greater than 2 second, I must be a constant. It will not change, and that thing has happened at immediately after t equal to 2 second. And here at t equal to 2 plus, current was 10 ampere. Therefore, inductor current will remain 10 ampere. So, this is t equal to 0. This is a very interesting problem, interesting in the sense that it will only enhance your handling, knowledge of handling inductors, how it behaves under different switching conditions. For example, current has to be continuous when you do switching. For t less than 0, current was 0. It is a good practice you draw also what was current t equal to 0, because it was open circuited, no current. At t equal to 0, you close it, then you say that current has to rise from this. Then you say L di dt is equal to 10 volt. Therefore, solve for I, which is very easy, di dt constant, I will be like this. Then use this boundary condition, I 0 minus is equal to I 0 plus is equal to 0, which is same as I 0, and you get that constant A to be 0. So, I t will be 5 t here, that is fine. Current was growing like this. For a practical circuit, it will not happen like that. Inductor may burn if you just keep pressing this 10 volt constant across the inductor. Suppose the rated, so at 2 equal to 2 second, suppose 10 ampere is the rated current, you decide that you move the switch from A to B, switch is moved like this, then from this to this. So, move the switch to position B. In that case, for t greater than 2 seconds, this is the circuit. So, now you see the impressed voltage has changed. It was earlier a constant voltage, now you have applied a 0 voltage. Why I am saying 0 voltage? It is a short circuit. No matter what current flows, drop here is 0. So, terminal voltage across the inductor is 0, and I want to investigate what happens to this current, which was brought up to 10 ampere at t equal to 2 minus. I want to investigate that. So, I once again write down KVL equation for t greater than equal to 2, which will be 2 di dt is equal to 0, applied voltage is 0, and then from this I conclude I must be constant for t greater than 2, it has to be constant. But at t equal to 2 plus, it is already 10 ampere. So, that 10 ampere will be preserved. It should not in any way disturb us, because nothing is violated. If 2 ampere flows constant, sorry, not 2 ampere, 10 ampere it reaches. So, for t greater than 2, the thing will be this shorted and this current will circulate. Is KVL equation violated? No. Why? Because it is a constant current, voltage between these 2 points is 0, L d dt of 10 will be 0, and same current circulates. Now, by this example, what is the connection between the energy storing and this one? See, I have now made a circuit by which I will pump energy into the inductor, and what will be the energy stored? Energy stored in the inductor at t greater than equal to 2 will be half, because current is constant 10 ampere, half L into 2 into I square, that is into 100, which is 100 joules. 100 joules of energy will be stored, and so keep the inductor shorted for any time you like. It will be storing that 100 joule. So, it is as if a pot where I have pumped energy into the inductor, and inductor will, it looks like forever it will store that energy. And whenever you want to retrieve that energy, you have to make a circuit for that. We will come to that. Suppose at some time I ask myself, okay, this energy is storing 100 joules of energy, let me use this energy in some circuit. Suppose I want to heat up a coil like a heater, it can be done nicely. So, in any case, the important point that I want to make is current in an inductor is continuous. You do a switching at any time you like, at t equal to 0 or t equal to 5 seconds, whatever it is. The important point is when you do switching at a particular time, say capital T you have done a switching, then current at T capital T minus and capital T plus has to be same. That is the first thing. Then you have to write down the KVL equations in all the intervals to solve for the currents and decide yourself the nature of the current waveform, as I have done here. Got the point. So, this is an exercise which is very simple, but at the same time it is very important to understand that every step of it. And I am sure if you go through this problem, which is also simple, can be easily tackled, no big deal to solve this differential equation, very quickly it can be done, and but try to interpret the results correctly. So, inductor stores energy and this that. Next thing what I will do is this, I will take the famous problems which you have done so many times, at least in your first year course of circuit, but let us also do it here. For example, I have a resistance and an inductor. I will just indicate how to do it, and here you have a this problem I will I will indicate that problem since I have drawn. I think I should tell it a little later. Anyway, this is the thing. Suppose we have a circuit like this, plus minus E. E is a constant battery voltage, R, and del is the inductor. What I will do is this, I will close this switch at t equal to 0. For t less than 0, S was opened, S in open condition, S opened, S was opened. Since S was opened, so I draw at t less than 0, the circuit was just like this, R and L, nothing is connected. Therefore, current here for t less than 0 must have been 0. So, I 0 minus this tells me that I 0 minus is 0. So, for t less than 0, this was the circuit, it was open circuited. This battery was there connected this way, but no current can flow, no closed path E. Now, at t equal to 0, at t equal to 0, S is closed, S is closed. And if you close S at t equal to 0, then I will say circuit for t greater than equal to 0 will now look like this. This is R, this is L, this is A, E. So, it is instructive always to draw the circuit topology before you are switching and after switching. Before switching you have to draw it, because you must have a knowledge what existed for the current at t equal to immediately before the switching. that is the thing. Suppose I say this current is I t. So, for t greater than equal to t greater than 0, better write, not equal to also. So, at t equal to 0 plus, I must conclude that I 0 plus, since it has to be equal to I 0 minus, that is also 0, that is the thing, which is for all practical purposes I 0 is 0. Then I have to solve this circuit. Okay? How to solve this circuit? I have to write down the KVL equation. So, I say we know what is the terminal relation at any time t plus minus. This is I t. Therefore, I will say this voltage across the inductor is L d I dt, is not? This is the polarity. And then you write down the KVL, minus to plus E, then plus to minus R I, then minus L d I dt, and you have come back to the same point, loop is closed, and then you say that L d I dt plus R I is equal to E. This is the differential equation, first order, constant coefficient, R L are constant, E is also constant. So, we will be able to solve it. I will devote some lectures on how to solve differential equations, but anyway this is so simple, I will do that in my next lecture, and also start looking at capacitors. Okay? Thank you.